This module covers lag controller design. In our 7 steps we've been following in the course, we're doing step 5, designing a controller in the S-plane. Our options for step 5 are listed here. The controller is the blue block in the forward path of the diagram. We started with the simplest form, making the control a constant number. The root locus showed us all the possible damping ratios and natural frequencies achievable using a constant number, also known as a gain. We mentioned integral, PI, PD, and PID controllers, but we're choosing to instead add pole zero pairs, neither of which are at the origin. In the last section, we covered lead controller design. Lead controllers have the same effect as PD controllers. We saw that lead controllers quicken the response of the system, which is generally desirable, but can worsen steady-state error of the system, which is not desirable. Lag controllers have the same effect as PI controllers. They improve steady-state error, but can slow down the system response. Before we give the design steps, we need to 1. Define what's known as the system type. 2. Define what steady-state error is mathematically. 3. Look at responses to 3 different input functions to the overall system. 4. Define 3 error constants. And 5. Ultimately build a matrix that clearly shows the control engineer all the possible steady-state errors achievable. We know there are many forms of the transfer function. There's the ratio of polynomials with the various coefficients for the powers of s in descending order. We know that any polynomial can be factored into n or m factors, and that those factors will have either real roots or complex conjugate pairs. This time, we'll use a modified version of the factored form where we factor out all the z and p numbers. Remember, all forms are mathematically equivalent. We pick a form based on a specific task we're trying to perform. By factoring out all the z's and p's, we know we no longer have coefficients of 1 in front of each s. The new coefficients are either 1 over the specific z factored out or 1 over the specific p factored out. We know that 1 over z, or 1 over p, is defined as the time constant, at least for factors resulting in a real root. Therefore, we'll choose to treat the new coefficients of s as time constants and define them using capital T's with a numbered script of either z or p, depending on whether it's a numerator or denominator factor. Since all the z's and p's factored out are real numbers, the overall gain, or constant multiplier of the transfer function, is now the original gain, k, multiplied by the product of all the z's factored out, divided by the product of all the p's factored out. We'll use k hat as the new overall gain of the system, and the mathematical definition is shown, where the capital pi symbol means product. Recall that mathematicians use capital sigma for summation and capital pi for products. So why go through all the pain of defining a new transfer function form? We'll soon see that to quantify steady-state error, we'll need to apply the final value theorem, which involves calculating limits as s goes to 0. This convenient form results in all the factors going to 1 as s goes to 0, leaving only the overall system gain of k hat. The one remaining item we haven't accounted for is a free s at the origin. So let's examine what happens for systems with one or more free s's at the origin. We'll use capital N to define the number of free s's. Little n will define the number of factors not at the origin. So this means the order of the denominator is now capital N plus little n. Control engineers refer to the number of free s's in the denominator as the system type. If capital N is 0, it's a type 0 system. If capital N is 1, it's a type 1 system, and so on. It's important to know that system types apply to the open loop transfer function. And also note that we said nothing about any free s's in the numerator. Recall that the steady state response of a system is that portion of the response that remains after the transients have died out. So, we're looking far downstream in the response timeline. Steady state error is the inability of our system to follow or achieve what we asked for in our reference input. This is sometimes referred to as tracking error. It turns out that the steady state error will be dependent on the kind of reference input we use. Let's look at the block diagram to write down what error is mathematically. We want the system output to match the reference input. So the error on the block diagram is simply the output of the summing junction, or R minus C. Let's divide the error by the reference input. Why? Because mathematicians like to manipulate functions to prove a point. Dividing both sides of the equation by the reference input brings the closed-loop transfer function into the analysis. For the given block diagram, which happens to be in cascade form, we know the closed-loop transfer function is g over 1 plus g. Let's substitute that into the equation. We need common denominators on the right-hand side, and when all the smoke clears, we get 1 over 1 plus g on the right-hand side. Now let's isolate error on the left-hand side by multiplying both sides of the reference input. These math tricks are common. We start by dividing both sides by something, do some manipulation, and then multiply both sides by the thing you divided by earlier. So the error is 1 over 1 plus g in the square brackets multiplied by the reference input. We just proved that the error depends on the kind of input. The only other variable in the equation is the open loop transfer function g. Steady state error occurs far downstream in the response timeline. So we need to apply the final value theorem. Recall the final value of a function of s is the limit as s goes to 0 of s times the function. Don't forget the s. When we substitute the error function, we get the right-hand side, which, as we said, depends on the reference input r, as well as g. The three inputs we'll examine are the unit step, the ramp, and the parabolic input. They're the first three inputs after an impulse on the Laplace table. As mentioned in class, the step and ramp inputs are easily done by a computer or a human operator using a control stick or a steering wheel. Next, we'll define what are known as error constants. We'll define three error constants. To help understand these, think in terms of a mechanical system. If the output is position, then the first derivative is velocity, and the second derivative is acceleration. In fact, we'll use the subscripts P, V, and A in the definitions. Consider the block diagram with a unit step input. We know on the Laplace table the unit step is 1 over s. If we substitute that for r in the steady state error equation, we get 1 over 1 plus g evaluated at s equals 0 on the right-hand side. We'll define the first error constant, k sub p, as the limit as s goes to 0 of g of s. In other words, g evaluated at s equals 0. Therefore, steady state error for a unit step input is now 1 over 1 plus kp. The value of kp will depend on system type. For a type 0 system, when we run the limit as s goes to 0, we get k hat. For a type 1 system, there's a free s in the denominator, so as s goes to 0, kp becomes infinity. With that same logic, any system type greater than 1 will also result in kp equaling infinity. Is kp equaling infinity a bad thing? Well, it depends where kp is in a function. For the steady state error function, kp is in the denominator. So, large or infinite kp is a good thing. In fact, infinite kp results in 0 steady state error. That is for unit step inputs. Kp will be the appropriate error constant for all step inputs. For ramp inputs, we'll define the second error constant. Plugging 1 over s squared for the ramp input into the equation results in a limit as s goes to 0 of 1 over s times g. We'll define the velocity error constant as the limit as s goes to 0 of s times g of s. Therefore, steady state error becomes 1 over kv for the ramp input. The value of kv also depends on system type. For type 0 systems, kv is 0. For type 1 systems, kv is k hat. For type 2 systems and higher, kv is infinity. And this results in steady state errors of infinity, which is really bad, for type 0 systems, 1 over k hat, which is at least finite for type 1 systems, and 0 for type 2 systems and higher. By now you should see the pattern of this analysis. The acceleration error constant is defined as the limit as s goes to 0 of s squared times g of s. And the steady state error is 1 over ka for parabolic inputs. Type 0 and type 1 systems result in ka equaling 0. Type 2 systems result in ka equaling k hat. And type 3 systems and higher result in ka equaling infinity. Here's a summary of steady state error for the various system types. This has been a long analysis of steady state error with respect to system type and reference input. If we summarize the results in a matrix, then we have a useful tool for the control engineer. Here's the matrix of steady state error with respect to system type, or the rows of the matrix, and reference input, the columns of the matrix. From this matrix, we can quickly see where we can expect steady state error to be 0, finite, or infinite. And remember, steady state error of infinity is really, really bad. Also, we can see that finite steady state errors get smaller as k hat gets larger. Finite errors are on the main diagonal. Above the main diagonal, steady state errors are infinite, and below the main diagonal, steady state errors are 0, which is the best case. You can also use this table to understand if your baseline system can handle a ramp or parabolic input. A type 0 system has no chance for either input. A type 1 system can handle the ramp but not the parabolic. Type 2 and higher can handle any of these inputs. With definitions of error constants and knowledge of steady state error, we now can go through the steps of lag controller design. Lag controllers reduce steady state error, but also slow down the system response. But many times in life, slow and steady wins the race. It just depends on the race, or in this case, the design requirements. Recall the effects to the root locus when adding poles or zeros. Adding poles pulls the locus to the right, which reduces stability, slows the system down, but improves steady state error. Adding 0 does the opposite. It comes down to the right combination, which is the art or science of control theory. Here's what adding a lag controller looks like. For lag controllers, the angle contribution on the polar plot, also known as phase, is negative. Like lead controllers, we're going to add one pole and one zero along with the gain Kc. For lag controllers, the pole will be really close to the origin, similar to integral control, and the zero will be to the left of the pole on the real axis of the S-plane. To make this work mathematically, one of our three design knobs, beta, needs to be greater than 1. We'll typically have beta specified or derived from a specification. Recall we used alpha in the same place for lead controllers, and alpha had to be less than 1. The other two knobs, the numerator time constant t and the gain Kc, will need to be determined based on the technique we use. Our technique will be to keep the phase lag less than 5 degrees. Here's the cookbook steps we'll use for this class. Step 1 involves drawing the root locus of the baseline system with no controller and determining the closed loop poles for a root locus gain of 1, which is the default. Step 2 has us calculating the appropriate error constant, which will be Kp, Kv, or Ka. Step 3 involves determining the desired increase in the error constant, which will relate to or depend on beta. In step 4, we'll determine the pole zero pair. In step 5, we'll draw a new root locus with the pole zero pair and a temporary Kc of 1. In step 6, we'll adjust Kc. We'll basically slide the pink box on the root locus until we get the original damping ratio from step 1. Step 7, the last step, always involves trying what we just cooked to make sure it turned out to meet our requirements. Next, we'll walk through an example. For this example, g is given as 10 times s plus 6 divided by s plus 10 times s squared plus 2s plus 2. We can determine the damping ratio and natural frequency of the baseline system by plotting the root locus and reading the data after clicking on the pink box. For k, root locus equal to 1. Or we can form the closed loop transfer function and calculate the information from the closed loop poles. For this example, the damping ratio is 0.4275. Remember this value because we'll need it again in step 6. For step 2, we have to apply some judgment to figure out what appropriate means. So let's say your boss says, focus on tracking step inputs. That means we'll need to calculate Kp. For this example, we run the equation and we'll see that Kp becomes 3. This results in a steady state error of 0.25 or 25%, and that's actually quite large. We know Kp was 3, and we need this to go up. It may need to be doubled or go up by an order of magnitude, which is a factor of 10. Let's say it needs to go up by an order of magnitude. We'll start by setting beta equal to 10 and see how this works. For step 4, we could use an ad hoc method like trying things using RL tool, or we can use the equation in the yellow box. Sigma CL and omega D come from step 1, and we pick a value for phi sub d lag. We can start with the midpoint of 2.5 degrees. The pole location is sigma z divided by beta. For this problem, we get a sigma z of 0.2694 and a sigma p of 0.0269, really close to the origin. Make sure your trig functions in your calculator or spreadsheet or MATLAB code are in the correct units. The equation uses both tangent and inverse tangent. The new open loop transfer function with the lag controller becomes what's shown here. Substitute sigma z and sigma p along with a kc of 1, and we get this open loop transfer function. Now, we can go to MATLAB and either use our locus or RL tool to draw the new root locus. For step 6, slide along the root locus until you see the damping ratio from step 1, which was 0.428 for this example. Notice that this gives us a Kc of 0.776. For step 7, add the new Kc. The lag controller is now fully designed. we have the new open loop transfer function and run the steady state error equation or look at the step response to figure out what we have. We see the compensated or controlled system has a lower steady state error, 4% compared to 25%. We didn't get the full order of magnitude improvement, but we did much better. So you could rerun the design with a larger beta. And the blue system is hard to see, but it is slightly slower than the original red system. So that was the price we had to pay to get lower steady state error. This concludes the module for lag controller design. I do want to make one note. MATLAB does not have a built-in command to generate a ramp response. You're going to have to visit my YouTube channel to see how to make MATLAB generate a ramp response by putting an integrator, 1/s, in series with the closed loop transfer function and then using MATLAB's step command.